Hey everyone, Professor Davis here for CHEM117, Experiment 7, which isn't really an experiment, Chemical Literature and Drawing. Now this is going to be a slightly unusual week for us, but we're going to cover a lot of material. We're just not going to be doing any exercise in the laboratory. Instead, we'll be using a computer and the internet to accomplish our goals. So some key topics for this week include, we're going to talk about sources of scientific information. We're going to talk about how we locate scientific articles using the internet, and how we can use those articles when we're writing papers of our own. Then we'll move on to talking about chemical drawing and some tools that are available to us. And finally, we'll go over some basic rules of drawing mechanisms, schemes, structures, and those sorts of things. In general, we break down chemical literature into three main classes. The first of these is primary. Now, primary literature is the original report of research as accounted by the person or persons who actually made the observations. It can cite the other primary literature directly, but again, it's primarily the work of the author who is reporting on it. And good examples of primary literature are things like journal articles and patents. Secondary chemical literature contains compiled or reinterpreted information. So it's reporting on the observations of other people, those who did not actually write the paper. They do, however, cite the primary literature directly. And a great example of secondary literature would include things like review articles, handbooks, and some textbooks, though not all. Tertiary chemical literature are what we call general knowledge resources, and they don't cite the primary literature directly. Therefore, the paper trail back to the original account of research is broken, and this is what distinguishes tertiary literature from primary and secondary. Of course, good examples of this would be your organic chemistry textbook or popular encyclopedias. So once again, to distinguish these three classes, primary literature is the original account of the researchers with an intact paper trail to all other references, while secondary is not the original account. It's reinterpreted information, but still contains an intact reference trail back to the original papers. Whereas tertiary is neither of these. It's neither an original account, nor does it have proper referencing to allow us to seek out the original paper by the original author. So how do we go about finding these primary and secondary sources that are so important to us when we create chemical literature? Well, we have a number of search and retrieval tools available to us, including web-based databases, such as the ISI Web of Knowledge, which scans a broad range of subject areas and gives us a very large database of journals to search. We also have slightly more focused search pages. For example, the American Chemical Society Journal's homepage, which will search only those journals published by the ACS, and therefore give us a more focused search on chemical topics. In a third instance, we have integrated applications like SciFinder, in which we can actually use other applications, such as chemical drawing software, to do a query based not necessarily on text, but on molecular structure itself. So when do we need to invoke the chemical literature in our writing? Well, the shortest answer to this is that when we rely on the work of someone else to make an argument, we have to give that person proper credit for their original ideas. And there's an example here in the middle of the screen. Let's say that you wrote this in a paper. The solubility of fluorine in methylbenzene has been shown to be 2 times greater at 304 Kelvin than at 283 Kelvin. Now, that's a very specific claim to make, and it implies that someone has made that observation. And since we haven't given our reader any indication that it wasn't us, the obvious implication is that this was our observation. But it wasn't. It was determined by someone else. So instead of simply stating this in our paper, we have to be sure that we give the author who originally made the observation credit Otherwise, we're plagiarizing them. Even if we have altered the text from the original source, if the idea remains intact, we have to apply proper referencing. So when we rely on the work of someone else to make an argument in our paper, we have to let our reader know that we're doing so. And one way in which this is done is by placing a superscripted number at the end of the statement. You can see here I've placed a superscripted 1 at the end of my assertion about the solubility of fluorine. So in the bibliography of my report, I simply list reference number 1 and then offer all the information necessary for the reader to track down the original account of research for themselves. So if they're unclear or aren't absolutely certain that I've interpreted it correctly, they can go back to the original account and form their own opinions about what these researchers saw and did and what it tells us. Now that we have talked a little bit about how we classify research and also about where we can go to find research papers, how these papers are organized, where the information goes, what each section of the paper is trying to tell us. This is an overall breakdown of what I call the anatomy of a scientific paper. And I should preface this discussion by telling you that there are as many ways to organize a scientific paper as there are scientists to write them. But there are certain fundamental principles to which we all adhere when doing so. So we're going to use a very simple method of organization, and you'll see many, many papers in the literature which don't follow this exactly step by step. But they will all adhere to the principles that are protected by using this format. We're going to talk about what's in the title and author credits, the goals of an abstract, how to craft a good introduction, how to convey a procedure, the methodology that we used, our results, our interpretation of the results called the discussion, and then how to summarize all of this in the conclusions, and finally, of course, to give credit to anyone else's work which we've used in making our arguments in a references section. So let's go one by one through these sections using a genuine example from the chemical literature and see if we can get a better understanding of what each one of these sections accomplishes. Let's start at the beginning, the title and author credits. You'll notice that in this case we're looking at a journal article from the journal Tetrahedron, a fairly high-level chemistry professional journal. And here we have a title and author credit. The title of this paper is Inhibition Binding Studies of Glycodendromer-Lectin Interactions Using Surface Plasmon Resonance. Not flashy, not cute, but very, very descriptive, and therefore very searchable. Whenever we title a paper, we never go for entertainment value. We only want to state exactly what our study covers so that our study is easy to find. The authors are credited in a very specific order. The order of the author credits always begins with the person who made the greatest contribution to the work. Then they're listed in decreasing order. Now in this case, there was only one additional author besides the principal investigator, so there's only one place for that author's name to be. Christian H. Schlick was the person who went into the lab and did most of the work on this paper. But next comes our exception to the rule, which is the very last name on the paper. This position is preserved for what we call the principal investigator, or PI. So in this case, I can tell that this work was done in the laboratory primarily by Christian Schlick with the guidance of Mary J. Cloninger, who also wrote the grant, obtained the funding, and has the faculty appointment, which made the work possible. One more piece of information that goes into the header is the institutional affiliation. Here we see that this work was done in the Chemistry and Biochemistry building at Montana State University. So Montana State University gave these researchers a place to conduct their research and resources, and clearly deserve some credit for that. So we always have an institutional affiliation associated with our author list. Now we're ready to move on to the abstract of the paper. An abstract is a brief synopsis of the project, all the way from its goals through its execution and results. We're not going to be writing abstracts for our formal reports, but if you stop and think about it, this is essentially what we've done for the first 6 projects that we've conducted in the lab course. So in the abstract for our paper, I can scan it very quickly and realize this is a paper about protein-carbohydrate interactions, which are important in biological processes, that the author is going to study them using surface plasmon resonance, and even that some of the values they obtained were in 260 to 13 nanomolar binding constant ranges. So it gives me everything from their system to their goals to their methodology and results, all encapsulated in a very, very short sales pitch. The next part of our paper is the introduction, which is our real setup for the reader to try to convince them to read the rest of the paper. We ask 3 questions during introductions. First, why is this work interesting in the first place? What is it that makes it relevant? Second, do we have a problem that we need to solve? And third, what is the solution that the author is proposing to that problem? If we can succeed in answering these 3 questions, we can usually encourage our reader to stick around and read the rest of our paper. Here you can see the authors state that protein-carbohydrate interactions are the initiating event in intracellular recognition events such as cancer cell aggregation, metastatic spread of cancer, bacterial invasion, fungal and viral adhesion. These are processes that are all very important in medicine. So clearly, this type of interaction is worth understanding. It's interesting. Next, the problem is defined. Traditionally, hemagglutination and precipitation techniques have been used to determine those interactions. Great. But these assays are limited in that they don't provide thermodynamic or kinetic data about interactions. The author has defined a very real problem. There's a shortage of information on this problem, which we've already decided is of interest to us. Finally, the author proposes how they're going to add to our understanding of this very important problem. In this case, surface plasmon resonance provides a valuable technique for accurately analyzing those interactions. So they've convinced me this is interesting because it has to do with infections. There's a problem in that we don't have thermodynamic and kinetic data about the interactions, and that this author just might have the solution in surface plasmon resonance. So now I'd like to read the rest of the paper. So let's do that. In many cases, the next section of the paper will be the procedure or the materials and methods section. This is where the author tries to explain exactly what they did during the study in a way that it would allow another trained researcher to duplicate their work. So the question you have to ask yourself when you're writing your procedure section is, am I giving the information and only the information that a trained scientist needs to reproduce my work in another laboratory somewhere else in the world? You can see here that the authors have used a lot of shorthand. So let's go through what all this means. Notice that the reagents are reported with their weights, volumes, and mole counts cited parenthetically. For this example, they've used a compound called 2,2-azidoethoxyethyl 2346 tetraacetyl alpha-D mannopyranoside. That's a big name. They used 330 milligrams of it in this step of their procedure. And as a courtesy to the reader to make the stoichiometry simple to follow, they've also told us exactly how many millimoles that is. Now, solvent volumes are reported, but we don't have to give mole counts because solvents aren't participating in any reactions. The third thing I'd like you to look at is down here in the second box. You see, they used another molecule called N-ethyl N-prime diethylamino-propylcarbodiamide. Now that's a lot to say, and that's a lot to write every single time. So in this case, the author has chosen to use an abbreviation, EDC. So they write the full name of the compound out, then parenthetically state the abbreviation they'll be using for the rest of the paper. And from this point forward, they can simply refer to N-ethyl N-prime diethylamino-propylcarbodiamide as EDC. This will save a tremendous amount of space in the paper if the author is going to cite this particular reagent over and over again. And finally, I'd like you to notice what's not there. The procedure does not contain mundane details about the procedure, such as the size of the flasks that they used or which corner of the lab they got the reagents from, because this is not useful information to a trained scientist. A trained scientist would know what size beaker to use to heat or manipulate a certain volume of liquid or solid. And furthermore, the reagent locations would be completely meaningless to someone working in a different lab. So it's all about economizing here. We want to get only the information that is required to get another trained scientist to duplicate our work. Now it's time to move on to the results section of our paper. So let's take a look at this page from our study, specifically this piece right here, because it illustrates two important points I want to make about what a results section should contain. First, notice that the section very clearly shows how the data were compiled and treated to reach certain calculated values. For example, see here they've got this plot that they used to convert their raw data into an actual binding constant. And second, that even though they report that binding constant here, see the observed KD for the binding of Con A to the mannose functionalized surface was estimated at 78 nanomolar. They make no attempt to interpret what that binding constant means or to compare it to anything else. So they're trying to objectively present their data without passion or prejudice in a way that allows their reader to formulate their own opinions about the study before reading the opinions of the study authors. Now we've reached the discussion section of our paper, where things are going to start paying off big, because this is where we get to have some fun and inject some critical thinking into the paper. So here's just a small piece of the discussion section from the paper that we're looking at today. And I'd like you to notice a few things. As you read through the entire discussion section, you'll notice the authors are beginning to present suggestions for how to interpret their data. They're not just reporting the raw numbers anymore. They're actually suggesting why the numbers are the way that they are. Notice that when necessary, they invoke other studies and compare and contrast their explanations and observations with those of other authors. And of course that when they do this, they have properly referenced that author's work. Notice that they've also offered their own interpretations. They believe the disparity in the binding constants occurs because Con A is able to bind multiple surface sugars. So they've offered a very specific explanation for why their data are different than something that's been observed previously by another researcher. What you'll also notice as you read through the discussion is that no new data or findings from their study are presented. They have already laid out all of the evidence and data collected in the results section. So while they might invoke another author's results for purposes of comparison and contrast, they will not invoke any new data from their own study at this point. The next section of our paper is the conclusions section. And I'm going to show you two small clips from the conclusion section of the paper that we've been looking at. And what I'd like you to notice here is that the authors cover two very important things here. First, notice they offer some commentary on whether or not they achieved their experimental goals, stating that their surface plasmon resonance competition assays are an effective tool for studying solution phase binding events. So clearly, they feel as though they've proven their point, that this technique does offer new information about the kind of binding events they've been studying. Second, they make some forward-looking statements about how their research can be improved, reapplied, or advanced. In this case, citing designing therapeutic agents for human health based upon the results that can be obtained from their assays. These are the two most crucial components of an effective conclusion. First, reflecting on your own work, and second, looking forward at how it can be carried onward for the betterment of mankind. And of course, the final section of our paper is the references section or bibliography, in which we give credit to those authors whose work we have relied upon to make our arguments. Take the example from our paper. The very first sentence of the introduction states that protein-carbohydrate interactions are the initiating event in aggregation of cancer cells, metastatic spread of cancer, bacterial, fungal, and viral infection. That's a lot to claim, and you've got to back that up somehow, and they have, in this case, with 4 different references, all of which are listed in their references section. And to be sure that any reader can go back and read those original accounts of research for themselves, they've indicated that they have 4 references, 1 through 4, and they've listed those numerically in their references section. So now, if I would like to read more about exactly what the authors were talking about when they said bacterial invasion or fungal and viral adhesion, I could simply go to one of these 4 references and read more from the original authors who made the original observation. At this point, I'd like to take a moment and talk to you about chemical drawing. As you peruse the literature, you're going to notice very quickly that no one hand draws anything anymore in professional publications. It's all done digitally. And we're very fortunate here at Georgetown to have access to one of the tools that those professionals use. It's called ChemDraw. Now, you'll find ChemDraw installed on the Blommer Science Library computers, and you can download a copy of it for yourself at the Blommer Library website. Search for ChemDraw. This is the software that you must use to complete this week's assignment, and hopefully will want to continue using throughout the rest of the course. If that doesn't do it for you, once you've completed assignment 7, you can try other drawing softwares as well, including BioviaDraw, which is a freeware. Another free version is called ChemSketch. And if you're a Mac user, you may want to try ChemAxon's product, MarvinSketch, which is Mac compatible as it runs in a Java applet. So again, this week, be sure that you use the ChemDraw installed in the Blommer Science Library computers or download it to your own. And in subsequent reports, I expect you to use one or a similar product to these chemical drawing softwares to create the images that you use. By far the most challenging figure that you'll need to draw during this course is a chemical reaction mechanism. Something like this example here, the second step of an enol ketone tautomerization. Now, each arrow, bracket, line, and letter conveys something very specific about what's going on during the reaction. So notice that I haven't included all the necessary lone pairs because I can actually infer what those are based upon the valence of each atom. So when I see an oxygen with 2 bonds to it, I know clearly that oxygen must have 2 lone pairs. Notice also that whenever practical, care is taken to be sure that elements of the drawing don't cross one another. For example, this arrow goes a long way around just to avoid touching anything else on the drawing, which could cause some confusion. So we'll be doing this for all of our drawings this semester as well. Although you're bound to find exceptions to this rule in the literature, this will be the rule for us for the course. Lines should never cross any other object within the drawing. With that said, with all the different arrows that you see in this mechanism, the question arises, which of these arrows should I use to depict which type of thing within the mechanism? Well, a straight, single-headed arrow depicts an irreversible reaction step, meaning one which does not establish an equilibrium, but rather converts completely into the product for that step. In the cases when we have an equilibrium mixture, we use arrows pointed forward and backward, above and below one another. A third type of arrow would be a single double-headed arrow, which is used to separate resonance contributors. And finally, the curved arrow tells us that we're monitoring the flow of an electron pair during the reaction. So in this case, the red arrows are depicting the flow of electrons, while the black arrows are depicting an irreversible reaction step and the separation of two resonance contributors within this mechanism. So what exactly do you have to draw for each report for each figure? And the answer is you need to draw whatever is asked for in the procedure for the week. It will specifically call for you to do at least one of these three things: either a mechanism, a scheme, or a structure. Now, mechanisms depict the flow of electrons as a reaction progresses in as much detail as possible, as in this example where we have a secondary alkyl halide being converted into an ether via an SN1 reaction with an alcohol. All arrows showing electron flow and reaction reversibility are present, and all the starting materials, products, byproducts, and intermediates are shown. In the case of a scheme, we show the starting materials and products of a reaction, but we do not show the exact flow of electrons. So in this case, we have the reagents, whether or not the reaction is reversible, depicted by, in this case, a single-headed arrow, meaning that it's irreversible, and products. Finally, when a structure, molecule, or compound is called for, you simply draw that structure as the figure within your report. As we'll see as the year progresses, there are situations which call for each of these three types of drawings. So be prepared to correct or to construct at least one, if not all three of these, for every report that you generate. This brings us to our list of goals for the week. First, we're going to find the most cited primary publication by a specific Georgetown chemistry professor using the ISI Web of Knowledge database. You'll be assigned a professor based on the first letter of your last name. Once you've retrieved that paper, you'll type a proper bibliographic entry using the Journal of the American Chemical Society's style. This is the same style that is depicted in your lab manual. Next, you'll locate a primary reference for use in the first experiment of CHEM117 in the spring semester, when we'll explore SN1 solvolysis. You'll do this using the Journal of the American Chemical Society's website, and once you've retrieved the paper, again, you'll type a proper bibliographic entry for that article in the style of the Journal of the American Chemical Society. Next, we'll use online resources to answer a few questions regarding specific authors, papers, affiliations, and number of citations, etc. Basically, I'm sending you on a literature scavenger hunt. And finally, you'll create an electronic drawing of a reaction mechanism using ChemDraw software. And again, this mechanism will be relevant to the first experiment that we'll conduct during CHEM117. So in a way there, you'll be getting double credit for this. Now, because all of these assignments can be carried out either on your own computer or in the Blommer Science Library, there's no need to report to lab this week. Instead, I expect you to spend that time working on this assignment, familiarizing yourself with how to search through the chemical literature and how to create good professional quality chemical drawings when you begin to generate literature yourself towards the end of the semester. That's all for now, everyone. I will see you the following week for our final lab experiment, and your TAs will see you in recitation on Monday.